Hey, hello, folks. It's in the afternoon. I'm about ready to drive home. So there are a couple of things that I'm going to go ahead and talk about in this video. I'm looking around to see who's looking at me. Okay, nobody is. All right, so I'm sitting in the parking lot, by the way. Okay, now, before I get to driving and you get to watch my elbow, you get to see some of the things that my face is going to do as I explain a couple of the topics I want to discuss today. And so we were in an earlier video, we were talking about the possible speed of rotation of the planet Earth, likely being at a faster rate of rotation, which might have been 16 hours, 34 minutes, respectively, maybe 4.4 billion years ago, or something to this effect, right? You can bet your bottom dollar that things that go around and around and around, like merry-go-rounds in outer space, do not always go around and around and around at the same rate of speed. Their speeds are going to fluctuate depending on how long the energy that forces them into that rotation exists at its own strength. So, and there was another thing I wanted to talk about. Let's see. Poop. Was going to, oh, right, that's right. Because we were talking about the Taklamakan supermassive volcano, and it is amazing. When I start to show the graphics, I know, I keep promising the graphics, but I'm not really that great at being a techie guy. So I'm going to try a new program, a different program, and see how well that works on my computer. I'm also going to buy a new computer because mine is just too slow to think, and sometimes it's pretty bad when I can think faster than it does. So anyway, if we talk about the Taklamakan, a supermassive volcano over in China, now we can go ahead and focus on North America. And in North America, of course, it's the volcano we're all familiar with that we refer to as the Yellowstone. Yeah, and it just so happens Yellowstone has two calderas within maybe, well, I don't know if you would call it two calderas inside of a bigger caldera, but it's an oval shape. If you look at it from space, you can see it. And it kind of looks like a link almost that you would see holding two chain links together. It would be, I'm not exactly sure what you call these types of flat links that have reams, two reams in them, you know. That's basically what it looks like. But I'm going to talk about how Yellowstone came to be what it is. A volcano, of course, but I mean, you know, what made it super, and what is it that we can, I'm pulling my socks up, by the way, that's why I'm getting close to the phone. I just want to get really close to you. No, okay, so anyway, here we go. Yep, got to pull the boomy fur off of me in case there's any extra boomy fur that was left over from this morning. It sticks to me all day. I don't know why I can't get rid of it. Okay, so anyway, we're talking about Yellowstone super volcano? Yeah, it is the super volcano, okay, and how it developed. So in the development of the Taklamakan supermassive volcano, I was describing how well, I don't have a better name for it right now, so we're just going to call it the Russian asthenospheric tsunami that came down underneath and pushed the crust of the earth up, because it wasn't actually, there was too much earth there for it to emerge above the earth surface as a semi-molten form of a wave of lava, like you see Japan sitting on, right? So in America, you get sort of the same thing, because there was the continent there. So the Nunavut asthenospheric tsunami slipped down and basically flowed south and west. It flowed south and then westward in a much more direct direction, going to the west, much more west than the tsunamis that you see and how they affected the terrain in Russia. There's more than one. There's like 3. Yeah, we'll talk about those later. The really cool one is just the one that created the Himalayas, right? Good thing we weren't standing there when it happened. Okay, so now that's what we're going to talk about. So it's going to be the Yellowstone, and one of the things I wanted to address that is the same. Now, we're talking about the trigger for all of these events was the Indonesian impactor, right? And the Earth is just covered with meteor impact sites. Whether or not current science or current scientists want to buy into what I have to offer, it doesn't really matter because they're there. So I'll go ahead and start with that, and it's from that we want to be able to determine exactly where the impactors originated from. So you have to think about it. If the galaxy is kind of like a frisbee, but it's not flying like a frisbee, it's flying like a jellyfish going through the ocean, or the sails on a ship flying through space, which is basically what it is, right? Then you know that it's moving in the direction that has, actually, believe it or not, it's moving in the direction of the lighter force, which is the top of the galaxy, so to speak, where we live, nice and peaceful up there, you know. And as it's going forward, it is striking material that may or may not be moving through space as it comes along that material within its flight corridor. And its flight corridor in this instance more than likely lies within a universal jet stream. Okay, so then you have the force behind us. Well, if we get pummeled from behind, that's because something that came to hit us from behind already had a very high velocity that was the energy transferred to it from some event far, far away, or maybe next door, who knows. But anyway, we did get pummeled from behind quite often. And that's why you see so many things down there in Australia, and why it is such a heavy impact area, right? So those ones are the ones that caught up to us. We weren't flying fast enough through the corridor. They caught up to us and smacked the crap out of us from behind. Well, and then the other way, it's the other way around. We flew into something that would just happen to be in our path. Either it was traveling slower, traveling at some odd crosswind type of front as we flanked it, or something to this effect, depending on what forces drove it to fly in the direction it's flying, and so on and so forth. So I just said goodbye to Rich. Yeah, he's the other guy. So anyway, that's what we're looking at, and to do that, I'm going to go ahead and read it off of here, because I can't drive and read this stuff. It's too complicated. So to be able to figure out what the poo is of a particular impactor, you have to take a lot of things into consideration, and it's the exact same type of navigational information you have to take into consideration before you travel back in time. If you want to travel back in time, like I'm pretty sure I mentioned it already, you can't just sit in a machine inside of your lobby and make it go spin in circles, and you go back in time and you see all these white-haired creatures and things like that ended up, I don't know, living before the dinosaurs. I don't know, it's some weird thing, right? Oh no, wait, that was the future, never mind. Going back in time where I forget what he saw when he got back in time. Okay, so you don't sit in one spot, you have to travel. And in order to travel back in time, you have to do one thing. You have to follow the Mason's compass. If you don't follow the Mason's compass, you will never get to where you're going. You're going to go lost in space. Well, anyway. So how do you figure out where the poo of something is, or was, at the time that it had occurred? You have to know a lot of information. One, you have to know the axial tilt of, say, for instance, an impactor to struck Earth. You want to know what the Earth's axial tilt was at the time of the impact. You want to know what the Earth's axial cant was at the time of impact. So you can't just look at your two-dimensional view of the Earth and say, that's the axial cant. Excuse me, that's the axial tilt. It has a cant. If you want to be able to determine the three-dimensional type of view that you need to think and take into consideration for plotting navigation, you got to take it all in. So you have to do both, the tilt and the cant. Ecliptic. You have to know what the Earth's ecliptic was at the time of the impact. you have to know the rate of rotation of the Earth at the time of the impact. Was the Earth going 24 hours a day on a rotation, or was it faster at a 16-hour, 34-minute rotational rate? Precession, you have to know what the Earth's precession was. If the Earth got smacked by an extraordinarily large impactor, we'll just call it an impactor, and that impactor caused the Earth to rock, and the scores of Jupiterian stripes tell you that it had rocked terribly bad, then you know that something made it rock, and the precession of that particular event is going to be terribly erratic, and not in the shape of a circle, but more in the shape of an ellipse. I almost couldn't say that one. They're such tough words to say, especially when your tongue is stuck to your lips. Okay, so now you also have to take into consideration, and I'm telling you this in the order of precedence. If you take this out of the order of precedence, forget it. You're going to get lost. All right. That's right. All right, so now you have to take into consideration, what was the Earth's perihelion at the time, or was it at perihelion, or was it at the aphelion? Which one was it? And I'm not talking about apes. I'm talking about, I don't know, aphelion or something like that. I don't know. Perihelion's kind of easier to say. Aphelion, I don't know if it's aphelion or aphelion. I don't know, because I ain't aphelion nothing right now. No, I don't know. Okay, so then you have orbital coordinate, right? You got to know what your orbital coordinate of the Earth was around the solar system at the time that the impactor impacted. Was it in June? Was it in December? That makes a big difference. If it was in December, it was more than likely at the top of the solar system, as it is as it is oriented with in relation to the galaxy, right? So, and then basically the bottom portion of the solar system is more around the June time frame for us. Okay, now, and the last thing I wrote down is you have to consider the lunar coordinate, assuming the moon was there at the time. Oh yeah, that's something else I'd like to talk about. The moon wasn't catastrophic. It didn't come to the Earth and just obliterate the Earth, and you see a bunch of molten blobs floating around in space and recoalescing, because if they did, the moon would not be in a tidal lock with the Earth. It wouldn't be heavier on one side and lighter on the other. And I'll go into explaining that later. It has a lot to do with clay. Have you ever worked with ceramics? I love ceramics. It's so much fun to work with. It's really messy though. It's very dusty, but my gosh, it's so much fun to sit there and carve little things out of the dirt. It's like, yeah, you got to try it sometime. Well, anyway, okay, that's basically the steps. Try to remember them. I hope you wrote them down, because if you didn't, I'm not writing them down for you. It's kind of hard for me to pass my notes. Well, here, can you see my notes? Okay, you saw them. Now, that pretty much takes care of that. Now you get to watch my elbow as I drive home. So I told you. Oh, why do we need to consider those things when you travel? Oh, I already mentioned that. When you're traveling back in time. You're going to get lost if you don't. So, yeah, nobody wants to get lost in space. That's a horrible thing to have to go through, It's very traumatic, especially when you're living in a submarine in outer space. As my wife referred to the spaceship, the Jupiter, spaceship named the Jupiter inside in that show, that the Lost in Space show, the new one. Okay, so I'm going to go ahead and go, and I'm going to have to kill this heater because it's like cooking me to death. And that brings me on to Yellowstone. So I can talk to you about Yellowstone. I might deviate and start talking about a few other things. I didn't really tell you how to travel back in time. I don't think I told you how to travel back in time yet. I did tell you that you can't do it by sitting in a telephone booth. So you gotta actually get up and move around, and you have to follow the Mason's compass. Hello, the Mason's compass. Maybe there's ooh, that sounds conspiracy type stuff. Mason's compass, that's why it's on the dollar bill. Our forefathers were trying to tell us how to travel back in time. Oh, come on, car, go over the bump. Okay. It's difficult adjusting to driving my car again after driving a forklift all day. I got up to the darn speed bump and my car stopped, and I just expected it to, like, you know, through its own drive, pull itself over the bump without me having to put on any foot pedal pressure, you know. Nope, that didn't do it. It just stopped. It was just sitting there, happy as could be. It was just like, you're just blabbing anyway. What do you care? All right. Well, now let me get back onto the subject here. Let's see. What was the subject we were talking about? Oh yeah, Yellowstone. So, and the Nunavut asthenospheric tsunami. All right, folks. So back in the day, who knows when that day was for real at this point, until we start taking core samples to get an idea. But the Nunavut asthenospheric tsunami is what created the Hudson Bay, is what more than likely created that little swirly pool, bayish sort of a thing on the eastern shoreline of the Hudson Bay. I haven't zoomed in on that to see what the name of that little thing is, or if it even has a name. But then it slipped down through North America. Now, you know, the funny thing about this is, at the same time, wonder why that guy flashed his brights at me. My brights aren't on. Oh, anyway. At the same time that the Nunavut was slipping down through the North American continent, underneath the continent, right? It emerged into what is now the Rocky Mountains. It basically, just like the Himalayas, the Rocky Mountains were pushed up from where they probably lay at earlier on. And then you see northern Canada up in the Nunavut territories, where all of those islandic masses of continental earth separated from Greenland and basically went southward and westward as they spiraled south and west. And it wasn't just the coefficient of solar wind pressure drag that accelerated this geologic event, but it was also the activity of the asthenospheric tsunami from Nunavut that helped pull that material down even farther, right? And then it would have been at the same time that Kamchatka would have pivoted clockwise, southerly or southward, and Alaska would have pivoted counterclockwise in a southward motion. So in pretty much the same way that the Magellan Strait basically wrapped around the Horn of Africa, you had a similar type of relationship between Kamchatka of Russia and Alaska. They basically pivoted southward and apart from each other. And the Atlantic asthenospheric tsunami swooped down, and its current was great enough that it was able to create, I don't know what you call it, a whirl curl into the Aleutian Island crest, wave crest, semi-molten wave crest, or whatever you want to call it, right? Whoops, I'm going a little fast for the conditions. So, now, in order to understand how Yellowstone functions, you might want to start thinking of it in comparison and in the terms of like human anatomy. And in this case, Yellowstone is more like an aneurysm, but it's a planetary aneurysm of magma, right? And basically, as time progresses, the magma just builds up and fills this pocket, and until the pressure starts to force the earth around this aneurysm to expand, and that's why it's rising, right? But that isn't really why it's rising. That's what is making it rise to an extent, but that's not the source. When you want to try to figure out in critical thinking, you want to try to figure in management and stuff like that, you want to go for the root cause. So just the continuous buildup of material, magma material under Yellowstone isn't in and of itself the root cause. The root cause is underneath the lithosphere, or maybe even partly in the lithosphere. So just like you have Ape Cave, which is like a 700-meter lava cave, lava tube on Mount St. Helens, you have a similar situation underneath, and it's the underworld, you might want to call it. So we all know that the mass of ice that lies beneath what we see above the surface in terms of icebergs is so much greater in mass. It's the same thing we understand as what we're going to look at underneath of the earth as well. So when you have things like the Rocky Mountains above the earth's surface, then you could imagine how much greater in mass the anti-Rocky Mountains are beneath the Rocky Mountains, right? And these greater masses of terrain have a huge effect on the way the asthenosphere flows. Oh, that guy. Thanks, dude. Okay, so that guy can't drive. All right, so anyway, you have this constant feed. So earlier on, I mentioned that the primary vortices, the equatorial vortices, are anticyclonic, so they're sucking material in toward the core, and the polar vortices are spitting material out. Well, inside the Earth, you have the same kind of process taking place. So as material from the Earth is channeled toward the core and spun upward toward the poles, it's recycled back around down toward the equator in this constant circulation. And as it circulates, it goes into the channel, the anti-channel that would have been created by the Nunavut Asthenospheric Tsunami, which gave birth to the Yellowstone volcano from the get-go. So it's still feeding that volcano. And as long as the volcano and the earth around the volcano is not frigid and it can give way, it will continue to give way and it will continue to grow. But it's not going to be able to grow much more before something gives. Either it starts flowing, it either begins to develop a shield volcano, which would be less fearful than other types of volcanoes, or not, and it'll be like the volcanoes we see in Hawaii, where it just oozes out ooze, or it could be catastrophic if the material around Yellowstone is more like Mount St. Helens and like the weld in a chain is stronger than the surrounding mass of material holding it into its place. So then we'll call that a plug. And so if the Yellowstone caldera is plugged, or worse yet, how about the Yellowstone caldera sister caldera to the east of the Yellowstone National Park? Yeah, that's right, the Yellowstone caldera where people live. That one might be a plug, and unless you get a core sample from it, we might not know if it is or not, right? But we could possibly imagine that as long as Yellowstone Park it behaves and operates like a relief valve from a water heater, then we have not so much to fear. But if we start seeing a sudden increase in the volume of geysers within that region, we have a problem. Or on the other hand, if suddenly Old Faithful stops shooting water, we have a problem. And we don't have much time to figure out what that problem is to find a cure for it. Now, the cure for something in that instance might be finding a way to create a vent, to engineer a vent that would relieve the pressure without upsetting the unstable conditions should they occur, right? And that's what you're going to get. You're going to have this constant flow of material going down in there to Yosemite. Oh, wrong. Oops, sorry. Wrong. I always get those two confused. Yellowstone. And Yellowstone's just going to continue to grow as long as that pocket is capable of holding the magma like an aneurysm. And that's what I would refer to as a I forget. I was mixing up some kind of geographical term with like lobotomy, like get away from the lob and put otomy on the end of some geographic term, right? To make it funny. That's probably what we would have to do. Punch a hole in that bugger and let that thing breathe and let it get rid of all that pressure. Kind of like what people do when you got a cyst. You got to kind of like poke a hole in it to make that stuff come out, right? Right. Anyway, I'm just taking my time here. Is that the guy I end up traveling home with all the time? No, that's another guy. It looked similar, totally different vehicles though. Yeah, so, well, that was quick. There you go, there's Yellowstone. All right. Now, when it comes to impactors, I can tell you right now that Chicxulub is way bigger than the current scientific community seems to be giving it credit for. In fact, it's in part responsible for creating a small portion of ridge in Central America. Sorry if I got quiet. I'm looking at traffic and I'm thinking to myself, well, what am I going to talk about next? I kind of like, I told you about everything there. Told you a little bit about Chicxulub. There's a much deeper story to the human epic than we understand. And, you know, we can either accept the things that we see on the earth and realize that because we can't explain those things, that doesn't mean that they don't exist. Right? Well, we'll just sweep those under the carpet for right now. And I'm talking about all those megalithic and, you know, ancient alien structures that may or may not have been ancient aliens. They might have been people on Earth. People on Earth that got wiped out after one of these massive impactors struck. And when you have an impactor that's approximately 8.4 kilometers in diameter, that has the magnitude and capacity to trigger worldwide events, geologic events, all at once, then you have an impactor that had the capacity to nearly completely wipe out all life on Earth. It definitely set the Earth back in time, right? And that might be why the Jupiterian stripes that I tried to establish based on the North Caspian Sea being the original North Pole of Pangaea, having to be completely theoretical, because at the time that the North Pole slip occurred, the North Pole was pretty much right where it is. That basic same area, right? So, the Earth had already started doing some different things up to that point. And all of that slippage could have definitely completely erased any scores in the Earth's surface, any Jupiterian scores in the Earth's surface that would have given us any inclination to the possibility of, you know, the North Caspian Sea actually being the North Pole. So, or maybe it's so difficult to find the evidence for this, and the reason I have to make it theoretical, because there were not any world-class impactors that had the capacity or the magnitude to cause the asthenosphere to leave scores behind. Because at that point the Earth was very fresh, so all of the continental mass would have been more of just even. It would have looked more like a cinnamon roll, or it would have looked more like what you see on the North Pole of Mars. Yes, the North Pole of Mars, that is continental mass. That is the fluff. That's the cream that went to the top of Mars when Mars was coalescing. Only thing is, it wasn't a big enough continental mass to start its spiraling southward, because it was balanced. It was small enough to be and retain balance. So it stayed there, and now Mars is almost like this really, really solid kind of a place. And it may not be solid at its core, but it's so solid at its surface that it doesn't have quite the tectonic activity that we do. And basically, I am deviating from plate tectonics and orienting myself and my thoughts and my theories more toward vortical tectonics. And I'm not the first one to come up with vortical tectonics. I developed that theory on my own, in my own interpretation of the Earth, and it just so happens that there have already been people who have had the same theories, but maybe they were short, similar, or the same interpretations of the Earth's surface in understanding what really took place. Maybe they were too confined by the scientific community's establishment of criteria. So much so that I understand how it is. If you spent your whole entire life being a scientist or working to be a scientist, you have a reputation to uphold. And when you have certain scientists going around tagging other scientists as essential crackpots, well, you know, that's just really not very fair. Especially when there might have been a time where, say for instance, a particular scientist who made that statement might have been at that time, or at an earlier state in his life, considered an essential crackpot for his theories. Well, you know what? It's just not right. You don't treat people like that. So for the scientists that spoke about vortical tectonics, they probably got squashed. And if they wanted to retain their scientific careers, they had to get in line, right? And that's kind of the advantage I have. I don't care what the scientists think about my theories. So if you don't like my theories, all right, too bad. I know, no sweat off my. So, yeah, that's a familiar term for some folks. I just didn't finish it. So I'm just saying, you know, if you want to be a good scientist, you really have to be open to the possibilities, even when they seem to counter or disagree with set criteria. Because I myself am setting criteria when I say things like the vortex is the cosmological, what did I say it was? The vortex is the, well, you know, brain fart, folks. I got to pay attention to the traffic here. It's about time for me to get off of 512 and go on I-5. What is that? I said the vortex is the cosmological common denominator. That's what I was trying to say. So I'm right, even in myself, I'm saying that there is a criteria. And the criteria is that pretty much everywhere you go and look through the cosmos, most things, if not all things, are striving to become vortical. And as long as you have variance in temperatures, you're going to have vortices. Period. Okay, so let's see, the other criteria that I made up was, well, I'm pretty sure I made it up, but maybe I didn't. Maybe there's somebody, I didn't read all of their journals, right? But let's see, the other one was, all DRCBs are gyroscopic. That's a criteria. Okay. All right, now let's see. I gotta go back to what I was talking about. I was talking about impactors. So the criteria, we need to lighten up on the impactor criteria, because what I want to share with the world, and all the scientists included, about the impactors that I see is that they are in fact impactors. And oh, by the way, yeah, I can tell the difference between an impactor and a volcano. Thank you very much. I live by volcanoes. Hello. All right. Well, anyway. Well, so there you have it. We're talking about anti-mountains and how they can affect stuff. Nothing worse than somebody in the right lane that's speeding up, and you can see them speeding up, and they're trying their darndest to prevent you from merging. Oh, whatever. Doesn't stop me. I still go. Okay, enough of that. Anyway, that's traffic. That has nothing to do. Well, maybe it does to some degree. I don't know. But, okay. But, well, let's see. What else can we talk about? All right, impactors, right? All those elements that we have to take into consideration when we decide we want to navigate back in time to actually arrive at the location that we want to be at the time when it occurred. Like, if I wanted to go back in time to Olympia, Washington, 4.4 billion years ago, I'm telling you right now, just sitting in the telephone booth next to the freeway isn't going to get me there, because I'm going to end up in a telephone booth like the TARDIS sitting in the middle of outer space, because the Earth is someplace else in the galaxy, which is someplace else in the universe, which is someplace else in the cosmos. So if you don't start taking that stuff into consideration, you're going to be a very terrible navigator. The same thing goes with impactors. I was explaining that you have impactors that strike that the galaxy basically flies into, hence the solar system flies into, and then you have impactors that strike the galaxy or strike the solar system from behind at a faster rate of faster velocity in traveling. Why is it so? Well, where's the traffic? There's nobody on the road. Oh, they must be all up there. Okay. Yeah, I see brake lights coming on now. I'm about ready to hit a stau. A stau. That's Deutsch. Deutsch for traffic jam. All right. So there I was, right? And I was haplessly traveling down the right lane on I-5, and all of a sudden, a big old pick-em-up truck went flying right by me in the center lane. Oh, I better stop weaving all over the place. Sitting there not paying attention to what I'm doing. That might be a state trooper back there. Nah, it's not. I don't even know what kind of vehicle that one is. It's just an ugly one. Okay, so not that the state troopers' vehicles are ugly. I like those ones. Those Ford whatchamacallits. I like. Oh, wait a minute. Maybe it is a Ford whatchamacallit. No, I can't fake this one out. This must be a newer model. Maybe it's a Mercury. No, it's a Ford. It's got that great big Ford ovally looking thing on it. Okay, so anyway, impactors striking the Earth. Yeah. You have to take all of those elements I explained in sequence to determine where the impactor's poo really was. Because if all you do is take the Earth's current obliquity in relation to, or the solar system's obliquity. Okay, let me go back. Okay, the Earth's, what the heck is that thing called? Okay, the Earth's ecliptic for today in relation to the solar system's obliquity in relation to the galactic plane, it's not really going to give you a true sense of the poo, especially of an extragalactic impactor, right? And ladies and gentlemen, not every impactor that strikes the Earth from one of our two asteroid-looking places, right? So you have the asteroid belt, and then you have the Kuiper belt. Well, that's not the only place where things come from that hit the Earth. We can get clobbered by anything from any direction, and you can bank on it. If you witness a supernova somewhere, the material blasted from that supernova, who's to say what its velocity is in traveling through space, right? But based on the distance, you can establish an understanding of what might be, how far the star was in terms of light speed, right? Now, from light speed, we can deduct the rate of speed and determine the distance traveled by that's kind of a mean looking truck. Okay, so you can figure out when something's going to clobber you. Okay, there you go. We're having to slow down up here. People are getting nervous. So, now let's see. When I talked about that, I talked about Yellowstone. Not really a whole lot more to tell you about Yellowstone. Oh, by the way, for all of those scientists out there that are swearing up. Now, I haven't checked the database that supposedly has 200 confirmed impact craters. I'd like to go through it and see what I see. But I'm telling you, if we're not looking at the Bermuda Triangle, and no, I'm not talking about the triangle, folks. I'm talking about the blooming circle that goes around the Bermuda Triangle. Hello? That's a crater, folks. It's a crater. Alright? Maybe not a really mean one, but it was mean enough to put the blast ring in the ocean, as large as it is, around the Bermuda Rise, which, oh yeah, by the way, is the central peak. Hello? Now, if our criteria indicates that a crater can only be a crater if there's a central peak, that's hogwash. And that is true, but for that to be the only thing is hogwash. There are craters out there that have far different and varying footprints of blast. And unless we start taking in all the considerations, because there is deflection through our atmosphere. So when impactors come through our atmosphere, they get deflected and they don't necessarily strike in terms of the absolute true trajectory that they struck the atmosphere in. So there is an element of error in determining the poo based on the blast information, but it's not going to be such a huge margin of error until you start getting super far away from the galaxy and it's extragalactic. Now you're starting to talk about a very huge swath of space where the poo could have come from, right? And who knows what it looked like back in the day. It won't look like it does today, I guarantee that. I talked about, did a little bit on time travel. I'm not really going to talk about how to travel back in time yet. I may have already said something about it. I don't know. I can't remember. That's Brian right there. That used to be my neighbor. Sold that house. Yeah, he's the incident response team guy for right in here in this little area. I should have waved at him, but he was coming up from behind me. Uh-oh. I don't know if I want to be behind this dump truck. He's passing me on the left. The trouble with getting behind those dump trucks is when they start throwing meteors out the back. Yeah. All right. Well, I don't know. I'm quite a ways away from home. What the heck else am I going to talk about? All right. Gotta fill up the clock. Now, what the heck could I talk about? Okay, fine. We'll talk about going back in time. Okay, so there's one way you can go back in time, and not necessarily. Well, you're basically still using the Mason's compass, but pretty much the Mason's compass is completely closed. Almost closed. So it's what we call the straight line distance time travel method. And that means basically, let's just choose 10 light years. So you want to go back in time, and all you want to do is return to the Earth at the location you were at the moment you departed the Earth, to travel back in time to return to the place on Earth that you were before you left it. You don't want to get there as you're leaving. That might create a problem. So you want to get there before you leave it, right? Which apparently also creates a problem. That's when you start getting into your, what the heck is it called? Paradox. Well, anyway, so there I was, right? And to do that, you have to travel 4.6 times faster than the speed of light in order to get back to where you were on Earth, at the location you were at on Earth at a time shortly before you left Earth, to go back in time to the point you were at on Earth before you left. Hope you can follow that. Okay, now let's say, for instance, we want to go back in time and we want to save those guys that were in that, what was it? The Operation something or other. Operation Pelican case or something. Operation Pennsylvania. No. Yeah, you guys know what I'm talking about. That sci-fi movie that came out, and that conspiracy thing about the U.S. trying to send warships back in time or some deal. I forget the name of it. Well, anyway. Okay, let's say you want to go back to save those guys before they get stuck inside the deck of the ship after they came back, right, to Earth after traveling through time, and they fell through the floor of the ship, and when they came back, they were half into floor and half not. All right. Well, in order to save those guys, you have to actually go back in time to where the Earth would have been at the time when that occurred in the cosmos. So you have to know where the Earth was in relation to the sun, in relation to the galaxy, in relation to the universe, in relation to the cosmos. And not necessarily in those simplest terms. Got to follow the steps, folks. Got to do it in sequence, or you're going to get it wrong. And you're going to end up like Rick and Morty, in the wrong place. Or you're going to end up with a whole bunch of Ricks. So anyway, that's how you do it. So the Mason's Arc, well, in this instance, I decided to change it, not to call it the Mason's Arc, but the Mason's compass. So basically, one point of the Mason's compass is where you were departing, and the other point of the Mason's compass is where you are going back in time, even if the other end of the Mason's compass is pinpointing the location you're standing at which is your point of departure, but yet that is your same point of departure is the point you want to go to back in time when the dinosaurs existed, right? You want to go to the same location, just back in time. Well, you still have to use the Mason's compass to get there. And that's going to be how you fly. You fly out toward the handle of the Mason's compass. I'm sure it probably has some technical term. I just don't know what it is. And then you're going to fly toward the pencil end of the compass or whatever, right? Or in this case, it's the two pointed stabby things that hurt if you poke them into you. Yeah. Now, okay, that mentioned that. You have to at least travel 4.6 times the speed of light. If you want to get there sooner, I suppose you could travel faster than 4.6 times the speed of light. The problem is traveling that fast without being obliterated or smacking into something you weren't planning on having been there when you smacked it, and it ended up getting squashed like a bug. Okay, so, well, that's why I think I already talked about dark matter. That's why you want to use dark matter, folks. Don't go flying fast like that through populated places like stellar clutches and such. That's a bad idea. That's like trying to travel down I-5 during traffic hour by 101 at 90 miles an hour when all the traffic is stopped. Everybody's passing me. I'm just really throwing a wrench in these people's spokes. I'm in the right lane, so they have no reason to have a wrench in their spokes. Yeah, that one finally got up the gump to go around. Timid fellow, I imagine. He didn't want to worry his passengers. It's one of those van pools, right? They'd be like, "George, you're driving like an idiot. Stop it, George. I am never driving with you again." That's really what they're saying to this guy, right? Okay. Oh, my gosh, I'm so far away from home. I need to pick up the pace. I have so far to go and not sure what else to fill up the time with to talk about. Not sure if I mentioned Little Tully Wooly. Yeah, that's right. Little Tully Wooly is an impact crater, folks. And that impactor had the capacity to set the conditions for, I think it's called the Great Coral Reef, that lies right on the perimeter of one of its blast rings. Alright, so, and it also may very likely be partly responsible for the coastal line of the eastern coast of Australia. Now, wow, this is awesome. There's hardly anyone on the road. Okay, so there you have it, right? Okay, now, the cool thing about Little Tully Wooly is that it's not like so many other impact craters. Little Tully Wooly is, in fact, a low-angle impact crater. So the projectile, or not the projectile, the impactor that struck the Earth in Australia at the time that this occurred, struck the Earth at a very high velocity, most likely, and from behind. So it was cruising, and it wasn't a cruise missile. I gotta watch the road. Quit looking at me while I'm talking. Alright, so now it was at such a low angle that it not only created a crater, a low angle impact crater, it also created a following subsequent ricochet furrow. Yeah, that's right, you guessed it. That's that great riverbedish looking thing that goes up toward the northeast. Yeah, that's pretty much where the impactor just basically plowed a hole in the earth Kind of like we see on all of our sci-fi movies. You know, every time we have a spaceship crash on a planet, it always ends up leaving this furrow, this impact furrow behind before it comes to a halt. Because nothing ever explodes like that. You know, that's only meteors to do that. Well, that's what you get. And that's what's unique about Little Tully Woolly. And then, of course, you have the series of 18 impactors that struck just south of Australia in the southeast Indian Ocean. And that was kind of like a meteoric Battalion 3 right there. There's some cool stuff about that one. So here's what happens, right? There's a lot of little crackety-doo looking roads going across the seafloor all over the world, and you only see them along the seafloor. Some of those I refer to as SRLs, S-R-R-L-S. Well, the S is plural, right? Or it's subterranean radial rift lines. And in the case of Hawaii and Tahiti, these SRLs basically branch out like a spider web from those islands, and it's not even the largest island of Hawaii that they come. It's the next one. It's what is it? Oahu. For some reason, Oahu is like the center of Hawaii's SRLs. And SRLs can happen from, basically in my mind, they can occur from like stretch marks where the earth expanded and then contracted. I'm thinking possibly. But what I'm seeing with things like the Southeast Indian Ocean Impactor impact series is that what happens is the impactors enter the ocean. They don't burst before they strike the ocean. They go into the ocean, and they don't quite make it all the way to the oceanic floor before they burst. So this is what we call marine bursts. So like air bursts, they burst midway through the ocean, in the ocean's water, okay? And their blast radius can be seen as a blast impact blast ring on the ocean floor. And in a lot of cases, the blast was so great that it completely completely blasted, like sand blasted, the sediment, the oceanic sediment, clean off of the oceanic bedrock, to the point where you can see the oceanic bedrock ripples. All right, now oceanic bedrock ripples were not created in this particular instance from the impactor itself. They were, because they're linear, they're not circular. Now if you see impact ripples, they're going to be in the form of the same impact ripples you see when you drop a pebble into a pond, a still pond of water. All right, they're going to go out in little rings. Well, you don't get that in the Southeast Indian Ocean. They're just basically straight lines. But normally those straight ripple lines are really not quite so straight. They appear straight, but they're not. And in a lot of cases, they're actually oriented in a perpendicular fashion, or a wave pattern fashion that has a center located in some cases at the center of the primary vortices, right? And that's where you get their orientation from. So anyhow, as some of these marine bursts occur, we're talking about extremely hot explosions taking place in a sometimes very cold environment of water. So you're having instant heat, impact, cold. Well, what happens when you get instant heat, impact, and cold around, ceramics and, say, for instance, glass? Oh yeah, the glass will shatter, ceramics will crack. Well, you get the same thing when these impactors burst above the ocean's floor, and that blast is so hot, it cracks the floor. It basically shocks the floor to the extent that it sends what I refer to as give me a minute, I have to get my mind back in order here. What do I call that stuff? I call those whip shock vanes, because not only does it become a vein that is severed from the rest of the ocean's floor, and when I say severed, I totally mean severed. The severance is so perfectly straight, it's incredible how straight it is. And it basically whips that severed vein like you would whip a whip to smack it and hear it go cracking at the end of the whip. That's why I'm calling it a whip shock. It's a whipping action of the vein of Earth that is sent through, just like a wave, sent from the impact center straight across whatever distance it's going in until something stops it. In this case, one of the Southeast Indian Ocean impactor blasts was so severe, it sent one of these whip shock vanes. First of all, it severed the vein, and the vein severage comes to approximately 16 kilometers. So this vein is 16 kilometers wide, and this vein travels across the Southeast Indian Ocean up to 1 million meters in distance before it strikes the very southwest corner, or the very southwest cape, if you want to call it a cape, of Australia. I don't know the name of it. And basically the continental mass of Australia stopped this particular whip shock vein from going farther. And that's another one of those effects you get. And you're not going to see these whip shock veins on the exposed surface of the Earth. It has to be under the water. All right? And you could probably see this occur, well, let's just put it this way. I do not see any whip shock veins stemming out radially from the Indian Ocean impact crater. So, no, excuse me, not the Indian, from the Indonesian impact crater. So chances are there's a possibility that when these impactors strike the planet and they become, subterranean ground bursts, if there is a whip shock vein, it got wiped the heck out by the blast. But the ones that are marine bursts are definitely going to have that shock that's going to give you the whip shock veins. And it just so happens that the particular impact shock zone, if you want to call it that I'm speaking of, has two other whip shock vanes extending radially out from that impact center. And it appears that the impactor itself, when it exploded, might not have left much behind because there doesn't appear to be any kind of a pop. And when I say pop, I'm talking about point of penetration, the pop. All right, now what else can I talk about? Doggone it, running out of things to say. All right, I already talked about time travel to the fullest of its extent. Talked about Yellowstone. Talked about the Mason's compass. Let's see. Talked about Little Tully Wooly. Talked about DRCBs. I'm pretty sure I talked about the dark matter and stellar nurseries. Which are related to stellar off-gassing. And as you can see, when I explain the way all of these things appear to have occurred, every last bit of information that I've shared, going all the way back to, universe types, is essential to understanding the simpler things that I'm trying to bring out and describe. And I'm going to download another program to see if it works better on my computer. I Googled it. I Googled what is the best game video kind of program out there right now, and this one site said that out of 7 top games, the toppest of the top is called OBS, or not games, but gaming video stuff is called OBS, Open Broadcasting System or something. OBS, no, not Suite. OBS, oh hell, what the heck was it called? OBS Studio. I'm going to try that one out and see if it works. The other program I was using, I don't know, it just didn't like my computer. My computer is really slow. I mean, I didn't spend a lot of money on it, so that's what you get when you don't spend a lot of money on it, right? But if I get this other program to function in my computer well, I probably won't go out and buy a new computer. Why blow money on another computer if the stuff you're using works fine? But if it don't, then that's it. I mean, 3 tries and I'm going to go try something else. Like buy a new computer that can actually handle that kind of stuff. All right. Because I really want to start showing everybody what it is that I'm talking about. Alright, yeah, looks like I'm going to be driving behind this big dump truck, and you know what? I'm not particularly fond of the idea of another meteor hitting my car, so I'm going to go around that guy. I don't even know why he's in that lane. Oh, because there's about 50 other million people in that lane. Oh, here I was. Oh, so anyway, once I end up explaining everything that I possibly could ever possibly... Oh, wow, that's repetitive. As soon as I get finished saying everything that I need to say to describe what I think of the universe, there's really not much else to talk about. But what I will be able to keep people informed of are all of the new impact craters I discover. And I'm going to measure them. And then I'm going to tell everyone where I think the poo was. But I'm going to do it the unscientific way, because I don't really have the toys to figure out all those steps of information to figure out a poo. But I might be able to tell you whether or not it was, the poo could have been extragalactic at the least, right? And I can definitely tell you, did it strike us from the rear? Did we get shot in the back? Or did we run into it because we were running too fast? I don't know. You're supposed to catch the ball, you're not supposed to bump it. Well, it depends. Depends on what game you're playing. If you're playing soccer, you're supposed to bump it. So, yep. Here, whoops. Yeah, I'm going so much slower than the trailer in front of me. Good thing you passed me. I wouldn't want to keep you from getting off the freeway sooner. Well, anyhow, let's see. We're ready. I'm trying to think of things to talk about. I already explained the universe. I already talked about how Bitsos might be more comparable to distributor caps in your engine. Oh, but I didn't really talk a whole lot about the Indus GRB. I don't think I did. I might be telling you all about that all over again. I think I did talk about that in one of my other videos. But what I didn't tell you is gamma ray bursts get pooped. I did tell you they get pooped. Yeah, I did tell you that. I'm not talking about that part of I did tell you. I'm going to